remind everyone that the open problem session is from 4 to 5. I've only heard from one person so far who's interested in giving an open problem. So I'm happy to get more open problems, and just let me know if you're interested in giving an open problem. Okay. And now we're going to get started with the afternoon session. We have the pleasure of having Thomas Bloom talk to us about the additive structure of sets of Fourier coefficients.
Thank you. And thank you for the invitation to speak here. Before I start, let me just say that essentially all of this is joint work with Olaf Sisask, if I don't say otherwise. And what I'm going to be talking about is the additive structure of sets of large Fourier coefficients. So first of all, I should explain what those are and get some general setup. So let G be a finite abelian group, and f is going to be some function from g to the complex numbers. So we're usually going to take g to be f2 to the n or something for simplicity. And then, of course, we define its Fourier transform to be the average of f times this character. So we're inside the dual group. And then the large spectrum for any eta inside 0, 1 is just defined to be the set of all characters such that this Fourier transform is at least eta times the maximum. Okay? And okay, so this conference is on the structure and pseudo-randomness, and so a common theme, especially when you're dealing with sort of linear additive problems, is you first of all express the problem in terms of Fourier analysis, and then you separate out the large coefficients, which here I'm calling the spectrum, from the essentially the negligible Fourier coefficients. And the large Fourier coefficients are the structured part, and the rest is the pseudo-random part. So in this talk, I essentially want to ask, and hopefully to some extent answer the question, what can this set look like? Okay. So in a sense, I want to ask, what is the structure that the set of structured parts can have? It turns out this is quite useful for various applications. And in particular, I'm going to limit myself to functions which are bounded, which is essentially equivalent to considering functions which are characteristic functions of subsets of the group. So I generally think about things in terms of this. So A is a subset of the group with density alpha. Okay, and let me just first record. Okay, so if we're trying to accumulate some facts about the spectrum, let's just record the first sort of trivial fact, which is the bound on this, how large such a spectrum can be by Parseval's theorem. So by Parseval, if I have sort of eta squared, alpha squared. So here alpha is going to be sort of the L1 norm of f because it's a characteristic function. So times at most the sum of the Fourier transform squared, which equals alpha. And so the size of the spectrum of A is at most eta to the minus 2, alpha to the minus 1. Okay, so that's the first sort of basic trivial thing. And even this turns out to be surprisingly useful in so many applications. Okay, so we can now ask the general question, if I give you a set which is at most this size for some eta and alpha, is it the case that there exists some set A I can construct so that this set is in fact the eta level spectrum of A, right? So this is sort of a trivial abstraction to very large sets being the spectrum, but if I overcome this, what more can I say? And it turns out there are essentially sort of three regimes of spectra that sort of you can think about them in. So the first regime is when the spectrum is very, very small. Right, say eta to the minus 1 in size. And then the medium regime is when the size of the spectrum is roughly sort of eta to the minus 2. And this is up to sort of log factors. And then you've got the large regime, when it's essentially as large as it can be. And it turns out that you sort of get slightly different behavior in each of these three regimes in terms of what actually can arise and what sort of phenomenon you can observe. So I'll do them in order. And the first is the small regime, which is sort of the most trivial regime. So let's first look at what happens here. So in the small regime, it turns out essentially this can be anything. So we really can't hope to say anything at all about spectra which are really, really small as sets, because they could be literally any subset of our group. So for example, here's a proof. Let sort of delta be a subset of G, size delta at the most e to the minus 1, and let f of x be equal to alpha times 1 plus eta, I guess real part, sum of gamma of x. Okay, now this is certainly, thanks to the fact that this is size of the most e to the minus 1, this is somehow like a real non-negative function, takes values in 0, 1, so it's more or less equivalent to a set. And so obviously the L1 norm is f equal to alpha, so you can just check. And also you can work out exactly what this Fourier transform is. This just equals to eta times alpha if gamma inside delta, and 0 otherwise, apart from the trivial character. Okay, so almost just by construction, you can just explicitly just write down a bounded function which has this as a spectrum. Okay, so that's all I'm going to say about the small regime, because it's pretty boring.
Characteristic 2, because otherwise you've got minus gamma as well.
Yes, sorry. Again, although I might write G, I'm implicitly thinking of everything being f2 to the n, so I don't have to worry about real parts and minus and plus. Everything I say is essentially true for general finite abelian groups if you correct them in the appropriate ways. But yeah, thank you. Okay, so that's sort of the small regime. So let me move on to the medium regime now. The medium regime turns out to be a bit more of an interesting and non-trivial case. In particular, this sort of easy construction just doesn't really work. I mean, obviously I can still write that function down, but it's no longer bounded. So it doesn't really fulfill the criteria. And it turns out that if delta is a set of, is a dissociated set of size e to the minus 2 log 1 over alpha. And by dissociated here, I essentially just mean same as linearly independent in the case of f2 to the n. So there are sort of no non-trivial additive relations among delta. Then there exists A such that the density of A is alpha G, and each level spectrum is precisely this set. Okay. So this is a construction which, in this context certainly, is originally due to Ben Green in around 2001, and it uses a version of what are called niveau sets, which were introduced for a different problem by Ruja in the 90s. And then this was sort of extended and refined in various ways by Shkvedov. The idea is certainly in f2 to the n is easy to describe. I just take A to be the set of all x, such that the Hamming weight of x is, say, a most sort of n over 2 minus big over square root n, or something, for appropriate choices of parameters. And once you've done this, you can sort of, well, at least this is the case if delta is sort of canonical basis or something. Which you can assume it is after sort of change of variables and a change of basis. And essentially A is this form. And for general groups, you can take it to be the set of all x, so that for all I, the real part of the sum over all gamma in delta I gamma of x is at least e to the minus 1, where I'm writing delta as the disjoint union of sort of log 1 over alpha pieces. And this is sort of the language that Ruja originally introduced in the integers. And sort of looking at this, at least you can sort of see why I expect this set to have density alpha at least, because this is sort of, I'm saying I have better than sort of square root cancellation, right? Because the size of delta I is roughly e to the minus 2. So sort of, what are the odds I have at least square root cancellation? Well, it happens with some sort of reasonably positive probability. So and I want this to happen for all sort of log 1 over alpha many times. So the density of A such that this is true is probably going to be roughly alpha. And you can also check, it's a slightly more involved calculation, that this does indeed have the right sort of behavior of Fourier coefficients, where you use the fact that it's dissociated. Okay. So that's the medium regime. And that's essentially what things can look like. And you might look at this construction and say, well, all right, if I have e to the minus 2 roughly dissociated elements, this can be the spectrum. What if I have more than e to the minus 2 elements? Can this be the spectrum? And the answer is no. It can't do better, which is a result of Chang. And Chang's lemma says that the dimension, by which I sort of mean the obvious thing in terms of it's the largest dissociated subset it contains. In other words, sort of everything else in the spectrum can be expressed as some of this many things additively. The dimension is the most e to the minus 2 log 1 over alpha. And sort of this sort of construction shows that this is indeed sharp. And this is the reason Ben Green originally did this construction, to show that Chang's lemma is sharp. I'll include the proof here. It's a really sort of very straightforward thing to prove, especially in f2 to the n, once you know the trick, which is that you use the following energy inequality, which is all right, by the 2m-fold additive energy of delta, I just mean the number of 2m sized tuples which have this sort of additive relation. Okay. So we have this sort of fact that if delta is a subset of the eta level spectrum of A, then the 2m-fold energy of delta is at least eta to the 2m alpha times the size of delta to the 2m. And I mean, sort of, there's a very nice one-line proof of this due to Holder. Well, sorry, due to Holder's inequality. I don't think Holder actually wrote this down, which says that. And what do? You use the fact that essentially I can write sort of e2m of delta as the 2mth power in the the Fourier side of whatever this is. So in particular, it's the physical side now because we're dealing with subsets of characters. So I can write this as and then you can get to this by Holder's inequality, starting from the fact that if I sum over all the gamma inside delta, this guy is at least eta times alpha and delta. Okay, so you sort of go from this lower bound to a lower bound for this with sort of one application of Holder's inequality. So this is sort of the crucial fact somehow about spectra that everything else stems from. The fact that we get a very good energy lower bound, not just to m equals 2, where this has usually been applied, but in fact for arbitrarily large m. And in fact, you want to take arbitrarily large m to prove Chang's lemma. So to prove Chang's lemma, I just let delta be a subset of my spectrum, which is maximal, which is a maximal dissociated subset. Then I have this sort of lower bound for the energy. But I also have this upper bound because I know that the only sort of additive relations are the trivial ones. So that's at most sort of m factorial times size of delta to the m. And I just choose m to be like log 1 over alpha, which is the optimal choice. So this sort of this eta squared here is what this eta squared here is coming from. And then the m is precisely killing off this one factor of alpha, which isn't growing with m. Okay, good. So that's sort of the medium regime. We're sort of very happy. Turns out that if I have size e to the minus 2, I can really look as bad as I can from the point of view of additive structure, in that I can be completely independent. So there's no additive structure at all, and that's pretty bad. And Chang's lemma says that, all right, if I get slightly bigger than that now, if I start to head more into the large regime, I'm sort of somehow leaving that behind me, right? So just to remind you, the large regime is when I'm thinking of this size of the spectrum, it's going to be eta to the minus 2, alpha to the minus 1 instead. Despite what the lighting may suggest, I do really care about the large regime. It's the most interesting one. So the first sort of, let me try and explain, all right, what sort of problem does the large regime come up in? And sort of the easiest one to explain in the sort of the canonical way is in Roth's theorem. And let me work in f3 to the n now because, right, I would love to be able to work in f2 to the n, but things get slightly too trivial there. So I'll work in f3 to the n because everything's sort of representative to write down. So the goal here is to count the number of solutions to x plus y plus z equals 0, with all my variables being taken inside A. And then sort of by orthogonality, I can write this as the sum of the Fourier transform cubed. I guess sort of normalized count of this is equal to the sum of the Fourier transform cubed. And then, as is sort of standard in sort of goes all the way back to Roth, and I guess in theory before that, it's the circle method. I isolate the part where gamma equals 0 from the part where gamma equals not 0. So I write this is equal to alpha cubed plus big O, gamma is not equal to 0, size of gamma cubed. And then in particular, this means that either there are sort of at least alpha cubed size of g squared solutions, which is somehow the random case, or I have sort of many non-zero large Fourier coefficients. Okay, so at the moment this is sum over all gamma non-zero, but the large spectrum will now make an appearance thanks to Parseval because sort of anything really small can't actually be contributing to this sum much. So by Parseval, the sum over all gamma non-zero, gamma not inside the alpha level spectrum, say of A, is at most alpha squared, if I'm not in the spectrum, times the L1 norm squared, which is at most alpha cubed. So in other words, it's negligible for appropriate choices of constants. So we eventually arrive at this, which is the sum over everything in the alpha level spectrum of A, Fourier transform cubed, is at least alpha cubed. Okay, so in particular, what can we deduce from this? And this is sort of how all these other proofs is essentially beginning with Roth, although in the integers rather than f3 to the n. This is sort of what they all get to. And then you look at this and sort of you have to extract something from it. And you want to extract something useful about the large spectrum of A. And in particular, this implies that the large spectrum of A is not empty, which is certainly a structural result of some kind, although a particularly weak one. But it turns out really that this is all, for instance, that Mechelen uses, that Roth uses, again in a different context, that Bourgain used in this first paper on Roth's theorem. And so in particular sort of gives you that a subset of f3 to the n without non-trivial solutions has size 3 to the n over n. Okay, and this was until 5, 6 years ago, sort of the best possible bound, just using this very sort of trivial information that the spectrum is not empty. But we can immediately do better in terms of what we can say about the spectrum just by dyadic pigeonholing. Right, especially if you don't care about factors of log. Okay. So, but by dyadic pigeonholing, we can say more, namely that there exists some eta between 1 and alpha, such that the size of the eta level spectrum of A is at least eta to the minus 3. Okay, which is already much stronger than saying it's not empty. And in particular, sort of, right, this can happen for any eta between 1 and alpha, but let's just look at the two extremes as somehow representative. So somehow if this happens to eta equals 1, then this implies that so the constant level spectrum is not empty, which is much more powerful than saying the alpha level spectrum is not empty. And indeed, this gives you a really powerful density increment result. Or if it happens at eta equals alpha, then this is saying the alpha level spectrum of A has size at least alpha to the minus 3. And by Parseval, that's in fact maximal. So in fact, we're in the large regime. So this is why I really care about what happens when a spectrum is as large as it can be. Because essentially, for instance, the application to Roth theorem on the capset problem, this is exactly what comes up. So either I'm very happy and I really win by a lot, or I have a large spectrum. So this is what I have to deal with now, objects of this form. And what's the goal when we're applying this? We're applying this in some sort of density increment framework. So we want, and you can in general show that if delta is a subset of the eta level spectrum of A, then there exists a subspace in F3 to the n such that in V, A has density, okay, the density's gone up, at least sort of 1 plus eta squared times the size of delta times alpha. Okay, so we sort of 1 plus eta squared times the size of delta is how much we've gained in the density by. And the codimension of V is at most the dimension of delta. Okay, and this is not too hard. You can just prove it using an L2 argument. And then, once you've got this sort of result, you then want to increment it. So i.e., we want, and what sort of density increment do we want? Well, we want this to be roughly constant as well, so then we have 1 plus some absolute constant gain. So the goal is to find some delta subset of delta eta of A such that the size of delta is at least eta to the minus 2 and the dimension of delta is small. And again, we can use the fact that in fact the size as a set, our spectrum is very large. Okay, so first of all, we should stop and remember Chang's lemma when we look at this and say, well, this is already sort of very suspicious because by sort of Chang's lemma in the constructions, I know that in fact I can have a spectrum which is roughly the size and where the dimension is the same thing as the size of the set. So how can you ever hope to do anything better than that? And this is where we stop and say, well, we can hope to do better because in those sort of constructions, our spectrum actually has, our whole spectrum has size e to the minus 2 as well, and we know that our spectrum's a lot larger. So there is reason to be optimistic here that we can in fact do better. And for this, we want to look at some constructions to get an idea about what might be true. Let's do constructions of large spectra. Okay, so how can we actually, if I give you a set of size, say eta to the minus 2, alpha to the minus 1, can you actually find a set A for which it is the spectrum? So how can we go about this? So the first type of construction is we might want to start by looking at the construction we had in the medium case and try and amplify it. So let A be a subset of F2 to the K, say, be a dense Nibbo set. So I know that, say, the size of its spectrum in this set is size roughly e to the minus 2. Okay, and then how can I make this spectrum bigger? Well, I can just sort of trivially just sort of put F2 to the K inside F2 to the N, right? Just sort of extend it on. And the point is, characters supported in the other coordinates aren't going to affect the Fourier transform at all. So the spectrum of eta of A, sort of the new spectrum, has become the old spectrum with a direct sum of F2 to the N minus K. Okay? And I'm going to write this as X direct sum H, where X is dissociated, right? Because I knew I could do this, right? This is my constructed in a dissociated set of size e to the minus 2. And H is a subspace. And what's the size of H? Well, you can just sort of check. I mean, the density of A is dense, right? So the size of A is roughly 2 to the K times some constant. So therefore, the size of H, which is 2 to the N minus K, is roughly alpha to the minus 1. So this is sort of the first of two examples. And note that the spectrum really is that large, so then the size of the spectrum really is e to the minus 2 alpha to the minus 1. So this is one way of constructing spectra which is sets as large as they can be by Parseval. Right, it can be a dissociated set, direct sum, a subspace. Okay. And there's a second type of construction as well, which is somehow really genuinely quite different. And I won't go into details, you can sort of do it as an exercise for yourself, but you can check that if I take A to be the disjoint union of roughly alpha to the minus 1 cosets of subspaces of size roughly eta G. So in particular, the site that A has density alpha as it should. You can check that for sort of appropriate choices of subspaces and cosets. The spectrum of A, in fact, looks like the disjoint union of roughly eta to the minus 1 guys look like this. So these are all cosets of subspaces, and they have size eta to the minus 1 alpha. I think this is like somehow genuinely quite different. So in this, I mean, another way to write this one here is this is sort of the disjoint union over all x of sort of h plus x. So these are also cosets of subspaces, but they have size alpha to the minus 1, and I'm taking eta to the minus 2 of them. Whereas here I'm also taking the disjoint union of cosets, but I have no information at all about the way these see each other, right? These aren't all translated to the same subspace or anything. They could be completely different subspaces. But on the other hand, I know that individually they're much larger. So this is somehow the two ends of the, I was about to say spectrum, two ends of the range that these large spectra can really look like. And I'll explain this in more detail in a few minutes, but this is it. In some suitable sense, we can show that if you're looking at spectra of genuinely this size, so eta to the minus 2 alpha to the minus 1, you're going to look like one of these two guys. So let's just sort of take that for granted by now and say that, all right, I know that definitely I'm going to look like one of these two guys. Does that mean I can sort of somehow do better than Chang's lemma? Can I find a large piece which is low dimensional? And if you look at both, you can see sort of yes. So in this case, I can find a piece. So again, let's take, we're thinking about eta roughly alpha. This application. So in this case, I can certainly find a piece, a subspace in fact, of size alpha to the minus 2. So like dimension log 1 over alpha or something. Okay, so this certainly fulfills this, and the dimension's really, really small. Okay, so that's really good. In this case, it's slightly more problematic, but still, if I take somehow like x primed plus h, where the size of x primed is roughly alpha to the minus 1, then the size of delta primed is roughly alpha to the minus 2, and the dimension of delta primed is roughly alpha to the minus 1. Okay, so this is still better than Chang's lemma, which would give you an exponent of 2 there instead. So this is somehow suggesting, if you believe that this is all that can happen, that you should be able to do better than Chang's lemma. And indeed you can, for this purpose. So you can show that there is delta primed subset of delta eta of A, such that the size of delta primed is at least eta times the size of my original spectrum. So I've lost something in the size, but maybe I can afford to do that. And on the other hand, I've gained an equal amount in the dimension. So this is somehow already a more promising structural result. It really is a refinement of Chang's lemma that's suitable for some applications, in particular applications where you're actually dealing with large spectra. For large spectra, essentially any problem where that's important, you can replace the eta to the minus 2 by an eta to the minus 1. As we'll prove this, so again, you can do it in the same way that I proved Chang's lemma earlier. You can use this energy bound. So again, you use this energy bound here. So eta to the 2m alpha times psi delta 2m. But rather than applying it to a maximal dissociated subset, right, and if I'm not applying it to a structured piece, I want to apply it to a random piece instead. So on a random, suitably chosen random subset of delta, very roughly, and then its details. Okay, good. So we had Chang's lemma, and then this construction said we can't do better, and then we looked at the fact that actually we have a large set, and then it showed that we can do better than that. So the obvious question to ask now is look at this and ask, well, can we do better? And this construction immediately shows the answer is no. Right? If my spectrum could genuinely look like this, it could look like a dissociated piece plus a subspace, and for that, you can't really do any better than this, right? If I want a large subset. If I want a large subset, I can't do better than dimension eta to the minus 1. Okay, but then we shouldn't be dissuaded. We weren't before. We should try and do better anyway. So try and do better. And let's just write down sort of the result that we wish were true, for instance, for now. So hope is that there exists some subset of my spectrum with size at least eta to the minus 2, say. Again, I'm always thinking about living inside the large regime. So the hope is that there exists some subset of my spectrum which is large as a set, and the dimension is like constant up to log factors. If we can prove this, we'd be very happy, right? It'd be a wonderful world. We can't prove it because it's false. But let's just actually think about these two examples again. In this case, we can prove it, right? Because it's true. So in this case, the size of the subspace is eta to the minus 2, and it's a subspace. It has dimension very, very small. And in this example, we can't prove it. But what do we notice about this example and the way we constructed it? In fact, H has size alpha to the minus 1. So in example 1, H is a low-dimensional piece. Right? So it certainly fulfills that. The problem is it's too small as a subset of my eta spectrum. But in fact, of course, it's not a subset of the eta spectrum of this set. In fact, it's a subset of the constant level spectrum of this set, because it's just trivial. It's like, for this construction of A, all the characters inside H give me a maximal Fourier coefficient. Okay. So, and H is actually inside the constant level spectrum of A. And so certainly this fulfills this criteria because now eta is 1, and so h is, well, size alpha to the minus 1, which is definitely bigger than constant. So if you if you relax the fact that we want this eta to be the same eta as we started with, if you're allowed to change eta somehow for the result, then this suggests that actually maybe that's possible to prove. And it turns out that yes, you can prove something like that. Okay, so sort of the slogan, I'll state slightly more precise things later. So let's call this sort of hope. Let's label this H for hope. So claim H is actually true for some eta primed, or at least eta. So in other words, if I start off with an eta level spectrum, I know it's really, really big, then I can say that there exists some level, I might have to go higher than eta, but that's fine, that's possibly even better for me, such that relative to that level, I get this really ideal structural result. So let me try and state some slightly more precise results now. Are there any questions before I do? A reasonable place to pause. So first let me state the structural result, or make some remarks about it. And this is a result along the lines of what I said earlier, that if you have a large spectrum which is very large as a set, it's either this or 1. You can actually say what it looks like. And this was the first result of this type was obtained by Bateman and Katz in 2010, where they used it to show that if A is a subset of f3 to the n without solutions, then the size of A is at most 3 to the n over n to the 1 plus c. So c bigger than 0. And essentially the way they did this was they proved somehow sort of a weak structural result along the lines that I said earlier. And then you can use the fact that if you have this sort of weak structural result, if you look anything like this, you're immediately very happy. And the other very extreme case, you can basically show you have a single large Fourier coefficient, which is enough for f3 to the n. So work with obviously SAS, we've sort of refined this and extended it. And so now we can say something like the following. If delta, if we have a large spectrum of size eta to the minus 2, alpha to the minus 1, say, then there is some delta between 1 and eta such that this spectrum is the disjoint union of delta to the minus 1 many sets of the shape xi direct sum hi, where xi has the size eta to the minus 2 delta squared, and hi has the size delta to the minus 1 alpha to the minus 1. And hi is a subspace. Just pausing to digest that a minute. So essentially, what you should think of is if delta equals 1, then this is precisely the construction 1 that I wrote down earlier, right? And this is x plus h, x has size eta to the minus 2, h has size alpha to the minus 1. If delta equals eta, then this is this other construction here, right? Because then x is nothing, it's not there at all. The hi's have size eta to the minus 1, alpha to the minus 1, and it's a disjoint union of delta to eta to the minus 1 of them. Okay, so somehow this is like an interpolating way, so I can sort of mix what examples 1 and 2, I can sort of mix and match them, which is why we get sort of this range, but essentially I always look like some combination of those examples. So at the moment, we can't actually prove this in as strong form as we would like. There's this annoying third case, sort of extra case, or there exists delta prime subset of the eta level spectrum of size, let's say, reasonably bigger than eta to the minus 2, and dimension reasonably smaller than eta to the minus 1. Without getting too precise about the quantification there. So the idea is that, I mean, obviously, if this happens, then we're still relatively happy, say, for applying it the way that Bateman-Katz did, because this is also really good. But somehow for a characterization, we want that not to be the case. It's kind of like a weird artifice of the proof. So I believe that this shouldn't be necessary. If you can get rid of this in the statement, then, for instance, you can do everything else I'm going to talk about, and then you get to prove a bound where you replace this by, say, something sort of bare end strength instead. So somehow all the knowledge is good enough already to prove bare ends type results for Ross theorem in F3 to the n. So without this sort of nonsense in brackets, you can in fact show that in sort of the capset problem, it's at most sort of 3 to the n times x with n to some, probably, definitely get a half. Okay, of course, at this point I should mention that we can in fact do much, much better, sort of unexpectedly last year. So the polynomial method of Kroot, Lev, and Pach, applied by Ellenberg and Hiswit, in fact tells us already that the size of A can be at most like 2.72 to the n or something. Sorry?
I think it's 2.756.
2.7. Then, yeah. That's enough margin for error. Definitely smaller than 3, anyway. Okay, but this is extremely recent, right? This has only came out last year. So somehow, all right, so even with this fantastic structural result, you can already do much better, but somehow the problem with the polynomial method is it seems to only really apply in this very rigid algebraic setting to the capset problem in F3 to the n. Whereas if we can prove a similar strength result by Fourier analysis, obviously that'd be great because Fourier analysis is much more robust and generalizable, and we know how to apply it to many different types of problem. So this would still be interesting. And somehow it's true modulo this annoying fact that I don't know how to get rid of now, but I see no reason that that's an insurmountable obstacle.
But with that, can you get something better for little c of Bateman and Katz?
Like the C would gets better. Yeah.
Can it be 1?
Sure. Eventually. I mean, somehow the problem is that there's a lot of quantitative dependence I didn't really write down here, obviously, right? Like by saying is, I actually don't mean is, I mean is mostly. By subspace, I don't actually mean subspace. I mean set with a small doubling. Like there's hidden stuff all over here, right? Somehow, but all the implicit dependence is polynomial apart from this factor here. And the problem is this factor here is already going to force you into a bound of this shape rather than that shape. The actual constant you get, you'd actually have to sit down and work out what the polynomial dependence was, just as if you cared about what this constant here, you'd have to worry about the polynomial dependence was. And somehow life's too short to track every application of Cauchy-Schwarz. So. Let me just say the proof idea of this result here. So somehow we want to, all right, the main goal is to extract these h's somehow and show they have this certain special form. And this is actually fairly similar to, in hindsight, it's an elaboration of the ideas that you can use to prove Balog, Zemuradi, and Gowers. Right? So in Balog, Zemuradi, and Gowers, what you start with is the assumption that sort of E4 of delta is at least the size of delta cubed, and then find some delta prime subset of delta, which looks like a subspace. Roughly. Okay, that's what Balog, Zemuradi, Gowers tells us. Well, as the way I've written it, Balog, Zemuradi, Gowers plus Freiman, Ruja. But if you actually look at the proof, certainly sort of the best proofs, best quantitative proofs known to date, then this delta primed has the form delta intersect some shift of delta for suitably chosen S. So somehow this is how you find extract a subset of delta with the appropriate amount of additive structure. Okay, we'd like to do something better than that. We'd like to do something sort of similar, extract some subset of our spectrum which has a reasonable amount of additive structure. Of course, the problem is this bound isn't true anymore, right? If you actually write down what our bound tells us, then it's like eta to the 4 times alpha times the size of delta to the 4, which is at least, because I'm in a large spectrum, this is really where you exploit the fact you're in a large spectrum, which forces this lower bound to be very large. It's working as hard as it can. This is at least eta squared times delta cubed. Okay. And I genuinely care about the regime where eta is non-constant, right? Eta is like alpha, or it's changing in size with delta. So somehow this doesn't really work. But the same idea does work with a lot of extra Cauchy-Schwarz, but all sort of elementary arguments. And sort of the trick is really you take our subsets are going to have the form delta intersect delta minus S. And note that somehow the size of this is already suggestive because E4 of delta is the sum of the delta convolution of S squared, which is like roughly equal to the size of delta squared times the expected value of such an H, right, which is roughly equal to eta squared times delta squared. So you already should suggest that if I take like a random S, then I know how big this H is going to be. It's going to have size roughly alpha to the minus 1, right? Which is precisely sort of what the theorem gives you. But the problem is, of course, and in Balog, Zemuradi, Gowers, you essentially do this and then you're done immediately because everything is so massive, everything's basically constant. You can play around with it and get it to work. In this, you can't, right? This is a fact you genuinely can't ignore. So how do you get around this and increase the amount of structure in H? You sort of take the intersection again with sort of the set of T such that the convolution of T is large. So somehow it's an interesting construction because I want a subset of delta, so delta intersects something. On the one hand, I go within delta, right? I look at some delta minus S and intersect that, and that gives me some amount of additive structure. On the other hand, I also want to consider H as a subset of the sum set of delta, and that forces a lot of extra additive structure. And so it basically ends up being of this form. And then you do this, and then there's a lot of Cauchy-Schwarzing and pigeonholing to find the appropriate S and T's and various case analysis, but this is what the set H looks like. This is somehow a way of getting the Balog, Zemuradi, Gowers type machinery and various things in additive combinatorics to work even when sort of your energy bound is much, much lower. And incidentally, the reason that there's this annoying extra case here essentially comes from in the analysis. We want to know that the size of these sets aren't too large, like these sets are relatively additively structured as well, which means you have to know that the higher energies of the spectrum aren't too big. And the only way we know to rule that out at the moment is if we can say, well, if the higher energy is much bigger than we expect, then all our other previous arguments work, like Chang's lemma type machinery and everything, all that stuff works really well, and so we can in fact say something like this. That's like a weird. That's like a weird artificial case that shouldn't actually arise. One should be able to just do the proof, and somehow everything cancels out at the end, because this is definitely true. But at the moment, I don't know how to do that. Okay, so finally, let me talk about how to get the result, which unfortunately I just rubbed off, which is how do you go from this information here to actually saying that there is a large subset with a low dimension of some level of the spectrum. At the moment, all I'm talking about here is the eta level spectrum, or some fixed eta. And to get around this, we use something we call spectral boosting. And the idea is that an additively structured piece of the eta level spectrum must lie in some larger spectrum. If I have a subset of a spectrum and I sort of get for free that it's additively structured in some way as a set, then I get for free that in fact the Fourier coefficients must be much larger on that set than I would naively expect them to be. So let me write down to give you an idea of. It's one of these things which I think is. It's more useful just seen as like a general technique rather than there's like not some easily packaged black box to just apply. But let me write down some sort of lemma. You can get an idea of what it says in some regime. So if we have the size of the alpha level spectrum, it's maximal, so it size alpha to the minus 3. And there exists some subset H inside the alpha level spectrum such that the size of H is roughly alpha to the minus 1, and the following things hold. So first of all, the relative energy between delta and H is maximal. Secondly, the energy of delta is not basically as small as it can be, given this energy lower bound. And finally, the Fourier mass of the total guy is at most alpha to the 4 times delta. So first of all, this H is precisely like the kind of H that you get as the conclusion of this structural lemma. So this feeds very naturally into that one. This result is essentially telling you that H is a subspace contained inside delta. This condition is essentially saying that this doesn't happen, right? So delta is as unstructured as it can be. And this condition is essentially saying that all of the Fourier mass of F is basically concentrated on delta. Now, those things might not be true, but if they're not true, then we win by other methods anyway, right? This is somehow the worst case scenario, these three conditions. So this is the scenario we're interested in proving things about. So what's the conclusion? This theorem. Then there is some translate of H. Well, I'm fine with taking a translate, it's still low dimensional, such that if I sort of take the L2 mass over H primed, then this is at least alpha cubed. And sorry, here I'm normalizing implicitly, so like the L1 norm of F is 1. So if you think about F as being the characteristic function of a set, then I've renormalized away the density. Okay, so in other words, i.e., this is saying that on average over H primed, which has size alpha to the minus 1, size of gamma is that's 1 up squared. It's like alpha to the right 1/2. Yeah, we normalize things away. In other words, H prime is a subset of the alpha to the 1/2 spectrum of F. So I started off just knowing that H was a subset of alpha level spectrum, but thanks to these extra structural conditions, I somehow get for free that some translate of H is, at least morally in terms of the L2 mass, a subset of the alpha to the 1/2 level spectrum. And note that if I let this be eta, then in particular the size of H primed is roughly eta to the -2. So this is basically what I mentioned earlier, that you can get a subset of size eta to the -2 with essentially constant dimension if you're prepared to change what you mean by eta, which, why aren't you? Right, we always are. Let me give you some idea of the proof. Again, it's proof idea. Again, it's very similar to sort of, it's Cauchy-Schwarz, right? Because what else can we possibly do in a proof? We start with a condition that, so delta convolved with delta, H convolved with H, is at least the size of delta, the size of H squared. I use the fact that delta is the alpha level spectrum to say that in fact the Fourier transform squared on this guy here is at least, so what is it, alpha squared times size of delta times size of H squared. Now if I just apply sort of the trivial bound to this, immediately I won't get anything very interesting, right? I get that the infinity norm of f hat squared convolved with H, but this is at least alpha squared times the size of H. If I just applied it immediately to that, which isn't very interesting, and so you don't want to do that. Instead, what you do is you don't apply the trivial bound here. First of all, you write this in physical space and apply Cauchy-Schwarz. So physical space, Cauchy-Schwarz, that implies that sort of this quantity here is at most. So again, there's a few lines, but I'll spare you them. You can sort of do them for yourself and check that what you get at the end is that the size of H, the L2 norm of this guy squared, times this quantity here. Okay, so it's sort of, this is the quantity we want to bound from below, and we've extracted something very, so this squared, I guess. Something looks very similar, but with an extra convolution by delta in there. And that's going to be really good, because now we can like profitably apply Cauchy-Schwarz to this in frequency space, because I'm assuming I have a good lower upper bound for the L2 norm of the convolution. So now, Cauchy-Schwarz in frequency space. So that means I have to bound things like the L2 norm of this, which I can bound by property B, and the L2 norm of this guy, which I can bound by property C, plus B and C gives me what I want. So it says that the L2 bound of this guy here is at least alpha times the size of H, compared to this sort of trivial alpha squared H. So somehow, rather than immediately trivially exiting here, I instead go to physical space, apply Cauchy-Schwarz once to get an extra convolution, apply Cauchy-Schwarz again in frequency space, exploit the fact that that convolution is somehow small on average to do, and then go back to my original setting, and I've sort of won a factor for free. Okay, and I'll stop there. Thanks.
Questions?
I have a question. Do you have an application to do this without the or part in the bracket?
Yeah, so the original motivation was to basically get the Bateman-Katz bound, which just went an F through to the n, to work for the integers. There's a very serious obstruction which stops the Bateman-Katz bound for working for the integers, which is that their method might end up with the possibility you only extract a single character which is a little bit larger than alpha. For the integers, that's just complete death. I mean, you can't win at all. So we came up with all this machinery essentially to say that you can always do better than that. You can always find the right amount of characters. So from a density increment point of view, it always just works. And in fact, everything works apart from a very annoying technical issue with ball sets. So we originally thought that we were done, and it was very complete. It turned out not to be done. So we think we have a way to do it now, but I'm going to be sensible and restrained and just say that hopefully this should give you bounds, similar bounds to Bateman-Katz in the integers, modulo an annoying technical issue with ball sets which shouldn't really exist.
Any other questions? No.
Sure. Can you, so for the case where the additive energy is on the other extreme, where it's very close to the minimum, so slightly say better than what the minimum is, is there anything you can say, or?
You mean if of a spectrum? So if the spectrum is, or just a general set?
The set, just like E4 of the set.
Oh, you mean the original set A?
Yeah.
Yeah, I mean, that's a great question. Essentially, because that's sort of the thing that we're using here, right? Where sort of, this is the, essentially, if f is the characteristic function of A, then this is the additive energy.
Yeah.
So we're assuming that this is small to be able to win. And if it's slightly larger than average, you can somehow win cheaply just by writing everything in Fourier space and dyadic pigeonholing again. And at the moment, that's all that we can really do. So like basically, I'm sure you can say more refined things. You should be able to say more refined things. But at the moment, we can only win by a relatively cheap trick in the regime that we care about, at least. But definitely, like there should be something like that. But I don't even know what the sort of the right thing to conjecture is, because you have to know before you guess somehow.
Okay, let's thank Thomas again.